What's up, scholars? Today we are going to do a centripetal force example. This is actually one of the more classic examples of where most people have heard of centripetal force, or sometimes they'll hear it called centrifugal force. Either way, the loop is one of the most famous examples. Now, you might have heard it called the loop-de-loop. My understanding is that it was originally called by like the people that did the circus and stuff, the loop, which is kind of weird. Anyway, here you can see people have actually scaled this all the way up to driving a car through a loop-the-loop. So the question is, how do they engineer this? How do they know going in that it's pretty likely the person's going to be safe? Another situation where you may have seen a loop-the-loop, kind of a famous one, besides like roller coasters and this car one, is a skateboarder named Tony Hawk. He's a little bit older now, but here's an example of, he invited some folks to check out his loop-the-loop, and here's a successful run. So we'll perhaps watch the whole video at some other time, but we want to kind of look at the physics of how do you make it through the loop successfully. So the first thing we're going to do is draw ourselves a loop. I'm going to pause and do that now. You can see I've sketched out a nice little loop here. We're going to go with the classic roller coaster example. So this, roller coaster car has come in with some initial velocity, and it's going to go around and out through a loop with a radius r. Now, we'll get to why this is in a moment, but the place that we're most interested in is what's the minimum speed we have to have up at the top so that we successfully complete the loop. Now, if we're going too slowly, all the group is going to do is get up to about here and then fall off. Instead, we want to make sure we make it all the way to the top, and then our momentum will carry us through the loop once we make it to the top. So I'm going to pose a question over here. I'm going to jot that down, and then we'll move forward with this example. So the question, again, that we want to address is, what is the minimum speed the roller coaster car can be going to make it through the loop safely? So to be clear, there's a speed, if you go too slow, you'll fall out of the loop, and then basically any speed above that, you'll make it successfully through the loop. We're going to start this one just like we've started many of these, which is we're going to use Newton's second law, but because they're moving in a circle, we're going to write it in our special centripetal force kind of way. So the way we're going to write Newton's second law in this context is going to be that the sum of the forces making it move in a circle, or the centripetal force, is equal to mv squared over r. Now in this case we're going to use the v squared over r versions because it's a lot easier in this context to measure the speed instead of the angular speed. So with that, what we need to do to solve this is we need to draw the free body diagram for the top of the loop. So if you look carefully up at the top of the loop here, there's going to be two forces affecting our car. The one force, which is perhaps obvious, is the weight force. Of course, weight is helping keep the car in the circle. And the second force that's helping is actually the structure of the roller coaster itself. It's actually the wood of it, or the metal or whatever. It's pushing down at all times. So that we could just simply call the normal force. I'll put a capital N there for the normal. I'm going to draw it on this side so we're not confused. So we've got the normal force, we've got the weight force. Those are acting together in some way to keep it moving in a circle. Now, we always have to pick our acceleration, and because we know that centripetal acceleration always acts towards the middle, I'm going to indicate off to the side here that the centripetal acceleration is acting downward. That's going to help us set this up. So the next thing we're going to do is take these forces and plug them in on the left-hand side. The left-hand side says add all the forces acting to keep something moving in a circle, and the answer will be mv squared over r, or the centripetal force. So let's do that. We've got the normal force, which is acting in the direction of acceleration. So I'm actually going to call that positive. Normal force is positive. We're going to add the weight force because it's in the same direction. And that's going to be equal to mv squared over r. Now, notice those are all in the same direction. I could, optionally, I'm going to do this in pencil so I can erase it. I could have said, well, normal force is down, so that's a negative. The weight force is down, so that's a negative. So the overall net centripetal force, that's also a negative. Now, I think it might confuse folks, so I'm just going to erase those as we go. What we'll do is we'll just make them all positive. Okay, so regardless of how you set it up, you should have all positives in here because everything, the normal, the weight, and the total centripetal force are all acting in the same direction. So I've just indicated there that the normal force, the weight force, and the centripetal force are all acting down in the same direction. Now this next part is a little bit of a conceptual hurdle, so I want to try to explain it carefully. We're trying to solve for the minimum speed to get through the loop. Right now we're saying basically you can go at any speed, but what we're going to do is let the car go slower and slower and slower until it just makes it through the loop. Imagine like a Hot Wheels set where you're just barely making the loop. At that case where you just barely make the loop, the normal force will very momentarily go to 0 at the tippy top there. The normal force will just go to 0 at the very top of the loop. So what we're going to do is we're going to say off to the side here, I'll put it in parentheses, when V min, the normal force goes to 0. Oops. So in other words, when you go through the loop at V min, you feel weightless at the top. So what I mean to say is that at the very, very top, the normal force will momentarily go to 0. So the normal force will be 0 at the top for just the moment that you're passing through the top of the loop. This will be still your weight force. Oops. So plus mg, and that equals mv squared over r. But now we're at the minimum speed that you could possibly go through the loop at. Notice, if you look carefully, this should just be a plus sign. If you look carefully, now our weight force is the only thing acting as the centripetal force. Now the only thing keeping you in the circle is your weight pulling you down, stopping you from going in a straight line. Now this is pretty easy. We need to just solve for the minimum speed to make it to the loop. So let's do some algebra. I've got an m on both sides, so we'll just simply cancel those m's. So we're left with g is equal to v squared, that's the minimum speed, over r. Now notice the centripetal acceleration when we're at minimum speed is just g. The only thing accelerating you is gravity. Now if we multiply both sides by r, I'm going to swap them as well. So we'll have v min squared is equal to g. I'm going to switch this for a capital R since we've got a capital R in our drawing, why not? And then finally we have v min is equal to the square root of g times r. So interestingly, the only two things that matter when we want to know how to get through the loop is what planet we're on, what's g, and the size of the loop. That determines the minimum speed. So to quickly review, the setup of this is just like any other centripetal force problem. That was what we were doing from the start. We started by realizing we need to use Newton's second law to answer this specific question. We set up a free body diagram, and then for this particular example, the conceptual trick is knowing that the normal force will go to 0 when we reach the minimum speed at the top. For any speed above the minimum, this normal force won't be 0, and this equation would look ever so slightly differently. That's all we've got today for this version of the loop. We'll take a couple of other looks at it as we move forward. Thanks so much.